Hello and welcome. Today we're going to be talking about a certain type of collision problem where you're going to deal with a force versus time graph. So let's look at this problem I shamelessly stole from the internet. We have two blocks that are colliding on a table. Block A is going to be sliding into block B, and they're both going to be moving off with some sort of final velocity after the collision. And here we have a graph of the forces of the collision itself. So this is time, and this is force. So without even reading the problem, let's think about what's happening here. So block A is going to hit block B, and the force is going to be zero up until the instant they touch. Once they touch, at a microscopic level, block B is going to be compressed like a spring, just a tiny amount. As it compresses, the force on it is going to increase up to some maximum, and then it's going to be steady for a period of time, and then it's going to be pushed away from block A, and that force is going to be going down. Okay? And then when the force is zero again here, they're no longer in contact. So this is basically a history of the collision in terms of forces. Okay, let's go ahead and read the problem. So block A has a mass of 2 kilograms. It's moving to the right on a frictionless table. Frictionless, that probably means there's no external forces at 60 meters per second. And it has a head-on collision with block B, which is at rest and has a mass of 4.5 kilograms as shown below. Part A asks us this. During this collision, the graph below shows the force of block A on block B. So what is the impulse applied to block B? Okay, so here's the situation. Block A is moving to the right at 6 meters per second. Block B, is equal to 0 meters per second. That's at rest. And it's asking about the impulse. Okay, I know impulse has units of Newton seconds. And I know that impulse is equal to the average force times the time interval of contact. So you might think there's not really much you can do here, right? So the time of contact is 0.3 seconds, and the maximum force is 40 newtons, but you can't multiply 40 newtons by 0.3 seconds because the average force is going to be less than 40 newtons, all right? In order to answer this question about the impulse, we have to do something called finding the area underneath the curve. So I want you to look at this. I'm just going to outline the x-axis here, or the time axis, excuse me. If I have this bottom part here, where force is equal to 0, and I have the actual curve, or how force changes with time. Let's say, for example, I wanted to find the total impulse between 0 and 0.10 seconds. Finding the area under the curve means just what it says. It's going to be this area. That will give me the impulse between this time here and this time here. That area would be in units of Newton seconds, okay? To find the total impulse during the entire collision, we have to find the area underneath the curve geometrically between 0 seconds and 0.3 seconds. So that means we want to find this entire area. All right, that's our job right now. Let's undo this. Okay. Well, to do this, we're going to make it. We're going to break this down into 3 different shapes. All right. We've got a triangle here. We've got a triangle here, and we've got a square between them, or not a square, but a rectangle. Excuse me. This isn't going to be too bad, actually. We know the area of a triangle is equal to 1/2 base times the height. We know the area of a rectangle is equal to base times height. So we can actually find the area of this figure. And the unit's going to be Newton seconds. Let's go and do that now. Okay, between 0 and 0.05 seconds, we have a triangle. The base is going to be, and you know what? Let's scooch down to this. Okay, so the first bit here the area is equal to 1/2 base times height. The base is going to be 0.05 minus 0. The height is going to be, well, the maximum altitude of the triangle, which is 40 units. Okay? And that's going to be equal to 1. 1 what? Well, remember, newtons are a vertical axis, time is a horizontal axis, so it's going to be 1 Newton second. All right? Now, what about that rectangle right there? Well, the rectangle's area is equal to base times height. So the area of the rectangle is equal to, well, the base is 0.20 minus 0.05. That's the base of the rectangle. The height is just going to be 40 units. Okay, we work that out, and we get 6 Newton seconds. In fact, I'm going to write 1 here and 6 here. And what about this last triangle? Well, that won't be too bad. It's just 1/2 base times height again. So we have 1/2. The base is going to be 0.30 minus 0.20. That's our base right here. And although it's off screen, I know the height is, the altitude of the triangle is just going to be 40 units. And this turns out to be 2 Newton seconds. So physically, what does this mean? That means while the force is ramping up in that first 0.05 seconds, the block B feels an impulse of 1 Newton seconds. During this period here, it feels an impulse of 6 Newton seconds, and during this period here, where the force is ramping back down, it feels an impulse of 2 Newton seconds. So the total impulse, the impulse on block B, is equal to 1 plus 6 plus 2, or 9 Newton seconds. But you know what? Another way to say Newton second is kilogram meters per second. So that's going to be the impulse, the total impulse felt by block B. All right, so we're done with A. Now, part B. What is the speed and direction of block B just after the collision? Okay, well, you know what? Its direction after the collision is going to be to the right. These forces, obviously, coming from block A, it's going to be pushing block B to the right. That's the contact force. So we know the direction is going to be to the right, but what's the actual speed? Okay, so for part B, we have to find the speed, and you know what? It's going to be using the impulse. Think about it. Initially, the block is at rest, so its momentum is going to be 0. So its final momentum will just be whatever impulse it had after the collision. So for block B, the momentum after the collision is equal to what? It's equal to that 9 kilogram meters per second that it got from the impact from block A. That's it. In other words, the mass of block B times the final velocity of block B is equal to 9 kilogram meters per second. What was the mass of block B, by the way? It was 4.5. All right, do a little bit of algebra here, and we get V after the collision for block B is equal to 2. And I'm going to just write B here, because we know this is block B after the collision. All right, that wasn't too bad. And now, the last part is going to ask this. What's the speed and direction of block A after the collision? Now, here's the thing. Block A is going to feel force in the opposite direction, Newton's third law. Remember, the opposite direction of this force on block B. So block A, during the collision, is going to feel a backwards force. So we don't really know the direction. The direction could be to the right, or if it feels a big enough impulse, it could be to the left. It could actually be bounced back off block B. We just don't know yet. But you know what we do know? We know the impulse on block A is going to be equal to -9 kilogram meters per second. Do you guys know why that is? Because the impulse is equal and opposite on block A. The impulse is equal and opposite to the impulse that block A gave to B. All right? So I already know the impulse. Okay, so scooting down to get some space, we're going to find the speed of A after the collision using the impulse momentum theorem. So using impulse again. All right, so our strategy is going to be this. We're going to get the velocity both from impulse and knowing the initial momentum of block A. We don't know this yet, but it's going to be pretty easy to find. So let's go ahead and write out an equation. So the momentum of block A before the collision plus the impulse felt by block A is going to be equal to the momentum of block A after the collision. Knowing everything we know about the relationship between momentum changes and impulse, this makes a lot of sense to me. All right, let's turn it into something more mathy. So mv before plus the impulse felt by A is equal to m v after for A. All right, but we know this is going to be -9 kilogram meters per second. It's a backwards impulse. Okay, now the mass of block A is 2 kilograms. The initial velocity of block A is 6 meters per second minus 9 kilogram meters per second. Remember, we're adding that -9. That's going to be equal to the 2 kilograms times v after, which is what we're trying to find. We don't know if this is going to be positive or negative yet. We don't know if A is going to end up going to the right or bouncing backwards to the left. So, you know, it's mildly exciting that way. So 2 times 6, that's going to be the initial momentum is going to be 12 kilogram meters per second minus the 9. That's going to be equal to the 2 times v after. 12 minus 9 is just going to be 3 kilogram meters per second. That's equal to 2 times v after. So conceptually speaking, right, this is the final momentum of block A. And it's positive 3. You know, it doesn't come out to be a negative. So we know it's going to be moving to the right already. Now we divide both sides by 2. And we get the answer. 1.5, we're divided by kilograms. 1.5 meters per second is equal to v after the collision. And I'll go ahead and write an A, so I know it's for block A. Okay, guys, and that's what we were required to find. Oh, and the direction? To the right. Okay, so we're done. Thank you.